Hello and welcome to Positive Physics. Today we are going to be looking at the wave equation and making sure that we've understood where it's come from and how to use it. So what's it all about? Well, firstly we need to understand some key information about waves. For example, what is the wavelength? What's the frequency? What's the time period? What's the wave speed? So let's go back to the wave on a string example and see if we can answer some of those questions. So here we go, we've got a wave on a string, and if you remember we have a source that's oscillating or moving backwards and forwards, up and down here, and it's producing this wave on the string. Okay, so it looks like a transverse wave. Remember, our energy is being transmitted perpendicular to the direction of the movement of the source. So our wavelength is the distance between two consecutive identical points on the wave. So you can see here, so we can either measure it from two peaks, two troughs, or two identical points, remembering that the wave must be travelling in the same direction at those points. And it's measured in meters. Now, frequency. F, given the symbol F. Alright, so again we've got our source moving up and down, and the frequency is measured in hertz. It's the number of waves which pass a point in a fixed point in 1 second. So if here we've got our finish, if we look at this point here, it would start a stop clock and say how many complete waves, how many oscillations pass that finish line in 1 second. So if it took 1 second for this whole wave to get through the finishing line, there would be a frequency of 1 hertz. Now, time period. Time period is related to the frequency, and time period is the time for one complete oscillation. It is measured in seconds, and if we have a look here, it's the time for the wave to have completed that whole section. So if that section took 1 second to complete, the time period for the wave would be 1 second. Now we need to link frequency and time period. So frequency is the number of waves per second, and the time period is the time for one wave. That means if one wave is produced every second, the time period of that wave is also 1 second. If two waves are produced every second, so the frequency is 2 hertz, 2 waves every second. 2 waves per second, hertz is like per second. Then the time for one of the waves is only half a second, because they made 2 in 1 second, so one must last half a second. Or if only half a wave was produced in 1 second, so if we had a frequency of half a hertz, the time period for one complete wave is 2 seconds. So if you can make half a wave in 1 second, you can make a whole wave in 2 seconds. So the relationship between the two values is that the frequency is equal to the inverse of the time period, or 1 divided by the time period. Now, wave speed. So the wave speed is measured in meters per second, as is all speed in physics, and is a measure of how fast the wave is moving. So that means how far the wave travels per second. So let's watch our wave travelling that far. Okay. Now that took 5 seconds. And if we assumed that the distance was 1 metre, then we would use the normal speed equals distance divided by time equation here, and we would see that 1 metre taking 5 seconds means that the wave speed was 0.2 metres per second. Now we need to link frequency, wavelength and the wave speed. So here we go, here's our source moving up and down. We have a frequency of 1 hertz. If we then move the source here, we move it up twice as fast, then we end up with a frequency of 2 hertz. If we move it half as fast as here, we would have a frequency of half a hertz. Okay, now hopefully you've spotted that something else about those waves has changed as well. The wavelength here we started off with, if we say that was 1 metre, look what's happened to it when we doubled the frequency. The wavelength has halved. It's now only half a metre because we've had 2 waves produced in the same amount of time. And if we double the time that it takes for our source to move, so we've halved the frequency, we have doubled our wavelength. So let's think about the time period, linking that back, remembering that's the inverse of the frequency. So the time period we've got 1 hertz will be 1 second. When we have a frequency of 2 hertz, our time period will be half a second. When we have a frequency of half a hertz, our time period is 2 seconds. Now going back to what we looked at before, the wave speed was how far the wave had travelled in a certain amount of time, or per second. So our wavelength tells us how far how big one oscillation is, and our time period tells us how long it took for that oscillation to be produced. And so if we divide our wavelength by our time period, we end up with the wave speed of 1 metres per second. But what do you notice? The wave speed for all these examples is the same. And that is because we have this relationship between the frequency, the wavelength, and the wave speed. When the wave speed is constant, then if you double the frequency, so in our second example here, you halve the wavelength. And if the wave speed is constant and you halve the frequency, you double the wavelength. So they are inversely proportional. We end up with the wave equation, where the wave speed in meters per second is equal to the frequency, which remember that just means per second, times the wavelength. So actually we can look at our units and it can tell us that it's the speed, because frequency is per second, so we could put per second here instead of hertz, and wavelength is meters, so meters per second. So here we have the symbol form, and it's important that you know the symbol form. V equals F lambda. It's useful because then you can write down your equation more quickly in an exam. So as the frequency increases, the wavelength decreases. They're inversely proportional when the wave speed is the same. Now, rearranging the equation. You must be able to rearrange your equations for your physics exams. It's really, really important. If we want to find this wave speed, it's nice and simple. We use V equals F lambda. If we want to find the frequency though, we need to remove this lambda. So we divide through both sides by lambda and we end up with the wave speed divided by the wavelength. Likewise, if we want to find the wavelength, we go back to here, we want to divide through by the frequency, and so we end up with the wave speed divided by frequency. Now, little exam note here. Often in exam questions now, they'll ask you to write out the equation. They'll give you the terms in words. So they'll say something like, write the equation that relates the frequency, wave speed and wavelength of a wave. And a lot of people then try and do it with the words in that order. So they would try and work out this equation here, where in actual fact the one they've learnt is that one. And I would say, write down the one you know. If they give you frequency, wave speed and wavelength, you can write the equation as wave speed equals frequency multiplied by wavelength. That is absolutely correct, and you'll avoid any errors as long as you stick to what you know and how you've learnt it. Don't try and think, or don't even think that you have to muddle things up. Just write it in the way that you know. So here's some calculations for you to try, 4 of them. Be careful with the 4th one, it's a bit of a warning. So pause the video now and have a go. So how did you do? Well, question 1 is quite simple. Speed of a wave, if the wavelength is 10 meters, the frequency is 2 hertz. We always show all our working. So we have the equation, V equals F lambda. We have 2 as our F frequency, 10 as our wavelength, so we have 20 meters per second. The wavelength, if its speed is 7 meters per second and the frequency is 20 hertz, again, write down the equation. If you haven't already done this, then you can write that down and then rearrange it. I've just rearranged it here. Wavelength is the wave speed divided by the frequency, 7 over 20, 0.35 meters. And then calculate the frequency of a wave if its speed is 300 meters per second and the wavelength is 1 meter. Again, write the equation, substitute in your values, give the answer and the unit. So here we have the wave speed 300 divided by the wavelength 1 meter, 300 hertz for our frequency. Did you spot the trap or did you fall into it? So calculate the wavelength of a wave if its speed is 1500 meters per second and the time period is 20 seconds. You've been given time period, not frequency. So the first thing you need to do is calculate the frequency. And remember, the frequency is just the inverse of the time period. So it's 1 divided by the time for one wave. So here we have 1 divided by 20. So our frequency is 0.05 hertz. Then we can use our wave equation, but because we want to calculate the wavelength rather than the wave speed, we write the wave equation down, we rearrange it for the wavelength, and then we can substitute in our values 1500 divided by 0.05, which is our frequency, and we end up with a wavelength which is very long, 30,000 meters. Okay, so hopefully you didn't fall into the trap, and hopefully that has helped, and you now are a little more confident with what the wave equation is and how to use it.